me. Yeah, as I'm already introduced, I would like to talk about AI systems engineering and how we can bring together engineering tasks with AI. And I'm super happy that we had that in the previous talk already, that things from different perspectives and different languages need to be brought together. So that maybe saves me a little bit of time. So I'd like to start with a short motivation. Typically, when you have these surveys from VDE or Deloitte or whatever, the outcome is pretty much the same here again. So a vast majority of companies say AI solutions will be important or very important for the overall success of our company, but only a minority has already been using AI in a way that it does that. And typically, the reasons for this are the lack of prerequisites, models, and data. And from my perspective, the most important areas in the industry where we can benefit from AI are the support of R&D tasks, so really helping the engineers to develop new and cool things, and that will be the main topic of this talk. And the other two areas are optimization of control processes or production processes, and the product quality, basically, the waste reduction and yield management in the end. So, and the main thing is, from my perspective, to bring together engineering and AI in some kind of framework that they can work together seamlessly in the same goal. So that I don't want in the end an AI engineer and a mechanical engineer or whatever doing their work, but I want to combine this somehow. I want to bring this together. And we published last year with Fraunhofer IAIS together in a white paper. You can find that somewhere in the internet. So it's KI engineering in der Produktion, where we basically defined this framework, how engineers and AI people might or should work together. And basically the goals are that they should, or we should, use AI as part of the whole engineering process. So it's not like we do the engineering first and then ask how we can add AI, or the other way around, but it should be somehow put together. And I hope I'll bring you a nice example how we did that together with Schaeffler. And to set the scene, I would like to talk a little bit about the general R&D context we are working in, especially in this case. And typically, we have an R&D, a very special situation. And that's one that you can only answer some questions when you make experiments, either physical experiments in the lab, like chemical experiments or things we will see later, or virtual experiments or simulations. And all of these things typically have one common denominator, which is that you only have a limited number of tests available, be it because you have a budget, be it because you don't have time, or you don't have the personnel. So it's always the discrepancy between I want to know as much as I can, but I can't do all the experiments I need to do to get that. And this is especially interesting or important when you have a high number of factors, because as you know, the higher the number of factors, the more the space you're searching for your solutions or for your problem increases exponentially, and that makes it really hard to pick the right experiments for your problem. And in the end, what you want to do with the R&D process, you want to generate a new product which is most effective or efficient or whatever, and this is in itself already a time-consuming process. And therefore, what we want to do is basically help people to minimize the number of experiments in the end. So, and how do we do this? So we choose an AI-based approach of experiment planning, and the idea is that you start out here with your overall plan. What should your product do in the end? For example, you might have a recipe and you want this with a certain attribute. Think of a detergent and you want it to wash 90% of your clothes clean at 30 degrees of Celsius, something like this. And then what we start out is we use expert knowledge from the engineers and typically historical data to build a machine learning model. And this is already the point where we bring together the expert knowledge of the engineers and the AI engineers, or the world of AI. And then what we basically do, we just run along their tasks. So we start out with the machine learning model. We then make a recommendation for the next trial, be it a simulation or an experiment. Then the engineers carry out the trial, analyze the results. We therefore, from AI perspective or the machine learning perspective, we just generate a new data point which can be fed back to the model, and then we repeat this cycle as long as needed. What does that mean? What I mean with that, I'll show you on the next slide. And in the end, when we're done with this cycle, we have basically a machine learning model which can then be used to produce or can be asked for the best recipes, for example, I need for my new detergent. And now, how does it look like? I have a small animation for this. So we start out with initial measurements. These are these black dots here on this curve, where this dotted curve is basically the ground truth we are interested in. And with these black dots, we've already fitted this bluish machine learning model. From this model, we derive a so-called acquisition function. This is something that can be chosen by the user in the end, and depends a little bit on what I'm looking forward to do. So will I optimize something? Will I just explore something? That's how I basically choose this acquisition function. And then I look at this acquisition function, find the maximum, and use this as a recommendation for the next trial. Here I just made this trial, that's the red dot. And the next step is then, so I perform these new measurements, and then I refit the model. And as you've seen, this model has already changed. Then the next step is I update the acquisition function, and then I do this loop again and again. And as you've seen, of course, this is a toy example that should look nice on a slide. But as you've seen, after some more experiments, my model is not perfect. You can see this on the left and on the right-hand side. It diverges from the ground truth. But in this area where I'm interested in, it becomes quite useful. And that's basically what we want to achieve in this scenario, where we just want to have a good prediction around the area we are interested in to optimize our products. And of course, we can further use this acquisition function to get more recommendations, and then in the end, we will have a nice overview of the whole function. But typically, this is not needed in these scenarios. So speaking of scenarios, the use case is like this. So what we want to do is determine a material property, which is called fatigue strength. And you can think about this as you have a piece of steel or any other material, and the question is, with which amplitude can I bend the steel so that it never breaks over the lifetime? That's quite important for certain applications. Think of rail tracks or something. When you have the steel is too weak on the rail tracks, the rails break, and then you might have a big disaster. So this is a really important thing to know when you design your applications or products which involve some materials. And what you typically do is that you determine this fatigue strength by the so-called staircase method, and that is an established method which is already described in the DIN norm and so on. And the basically idea is that you apply a certain amount of force to your steel, and in the experiments are then either they survive, that's called a run out, or they break, and that's a failure. And from that information and the information you might have about the properties of the steel, you have to determine this fatigue strength. So in our approach is basically to try to take into account the similarity of different materials and to take into account all of the data. Because the drawback of this staircase method is, of course, all these methods need to be tuned somehow. But in this case, you need to be a real expert to tune this. So you have to pick basically the right starting point for your experiments, and then it runs through. But this is something only an expert typically can do, and only you have only the so to say two neighboring experiments which affect each other. So the next experiment does not rely on all experiments before, but just on the last one, which is basically a waste of data in the end. And yeah, we wrote a nice paper about this, basically, where we proposed this architecture. So we start with the material parameters. We train a machine learning model. In our case, it's a Gaussian process model, because we use Bayesian optimization later on, or a variation of this. And of course, this is something where we need the AI expertise to find the right hyperparameters and to make it work back actually. Then we generate a prior distribution over our desired property, namely the fatigue strength. And then we design a special likelihood function, which is then used for basically three things. On the one hand, we get out the estimated parameters for our final fatigue strength, and in the same time, we can use this to make the recommendation where to make the next test, where we basically use the maximum a posteriori value of this distribution. And of course, this gets better and better if you add more experimental data. Now, as I told you in the beginning, we applied this with Scheffler, and they have basically exactly this challenge. So they have these materials, they need to determine this fatigue strength, and determining this fatigue strength is a quite tedious task. So you have, you can think about, again, this little material, these little specimens, and when you apply a very weak force on this, they can run forever. Yeah, because that's what you measure in the end, and that means at some time you have to stop, and what that boils down for the lab technicians is that these experiments can run up to 60 days. That for one data point here in this plot, and they can cost up to 12,000 euro, which is why you're really interested in reducing the number of specimens you want to look at. So, and basically what we did is to apply all these tools or all these bits for this use case. And what you can see here up in this part, that's basically the initial prediction model, so the Gaussian process, which just takes the materials parameters as an input and predicts already this fatigue strength we are interested in. This bit here is the likelihood function we tailored for this experimental setup, which on the one hand says, okay, what's the most likely value for the fatigue strength at the moment, and how good am I actually at determining it by giving the width of it. And here in the lower plot you can see the two basically approaches competing against each other. So all these violet and blue, green dots are the experiments from the staircase method, which basically have to be done in this way. And in this shaded area, that's that would have been the experiment which have been proposed by our method. And of course, they didn't want to basically run a new whole experiment, so we had to do this on historical data. But when we evaluated it, we saw that we could save roughly half of the experiments, which, as you can see, I mean, here are like 17 or 18 experiments, and when you save half of it with this cost amount, you can save just a lot of money just by applying this. So that brings me to my summary, and yeah, I hope I gave you a little insight in why it is useful that we should use AI as part of a systematic approach to engineering challenges. Then I hope I kind of convinced you that it is a useful approach in R&D challenges. And finally, I hope I really convinced you in the last bit that it worked in a real life application. So thank you for that. Here's my contact data. I will be around for the day later in the panel discussion, and we also have a Fraunhofer booth next to the Grace Hopper stage, I think. So thank you.